In the next few videos, we're going to take our Fourier series, which was an infinite sum, and turn this into an integral, and this will be called the Fourier Transform. So here, once again, is our Fourier series. So imagine some function which is defined over some finite domain. The convention we're choosing for this development is now going to be symmetric about the origin 0, so we've got from negative lambda on 2 to plus lambda on 2, and this function is periodic. So outside this domain, the function is just repeated and repeated and repeated. So we have the function defined over this domain. The longest period in the Fourier series that makes up this function will be lambda, which is the length of this domain. So we have the longest period functions will be cosine k naught x and or sine k naught x, where k naught is 2 pi on lambda. The lowest angular frequency in the series is therefore k naught, and each term in the series is separated by frequency k naught. So as you go up in the series, we have cos k naught, cos 2k naught, 3k naught, and so that's the separation in frequency in the series. So what if we want to model a function which is not periodic? Well, one thing we can do is make this domain longer and longer and longer. If this domain over which we are defining the series becomes infinitely large, then we have a function which is not periodic. So we can imagine taking a limit where lambda tends towards infinity. So in this case, k naught will tend towards 0, because k naught is 2 pi divided by lambda. And the frequency separation between the terms in the series will also tend towards 0. So if you remember before, we plotted a discrete spectrum of the terms in the Fourier series, the spacing between these terms will tend towards 0. So in this way, we can imagine that our series will tend towards an integral. In other words, here's our Fourier series, and as we allow the spacing between these frequencies to tend towards 0, which corresponds to allowing our domain of integration here tend towards infinity, then this sum will tend towards an integral. Now, one thing to note is that in the series, these values of Cn here, these are discrete values of Cn. Each Cn corresponds to a particular frequency Kn. When you head towards an integral over here, the Cn will become some function of k. And so for a particular value of k, some particular value of frequency up here, you have some amplitude given by this function f of k. And this f of k will be a continuous function of k. Whereas here, it was a discrete, it had discrete values that depended on Kn. So instead of these discrete amplitudes for each frequency Kn at intervals of k naught, we're going to have a continuous function f of k that gives the amplitude of the frequency k, and the intervals will be some infinitesimal interval dk, so it becomes a continuous function. So let's go through this step by step a little more formally. So here's our Fourier series, and here is the value for Cn, which is evaluated through this integral here. A couple of notes: we've changed the limits of the integration, they're normally expressed as negative lambda on 2 to plus lambda on 2 to plus and minus pi on k naught through this substitution here. Also noting that Kn is 2 pi n on lambda, and if you take increments of dkn, then you find that dkn is equal to 2 pi on lambda times dn. But the increment dn is always equal to 1. So we're going to use these increments in the next line below. I'll also note here there is a slight ambiguity in the notation I'm using, in that k naught here is given by 2 pi divided by lambda, but kn is 2 pi n on lambda. So when n is equal to 0, this is different to the k naught I'm using here. So this kn is used to indicate values of k for n not equal to 0. In fact, under this definition of kn, n equal to 1 would be equivalent to this k naught here. So slight ambiguity, I hope that's okay. Okay, so now as lambda gets bigger, if we look back at this increment here, as lambda gets bigger, then dkn will tend towards 0. So we may write our sum here is given by Cn e to the I kn x dn, where remember here our dn is just equal to 1. So n's an integer, so the increment dn is always equal to 1. But now we can substitute this dn here with dk. So now we have dkn instead of dn, and this factor lambda on 2 pi sitting there. Now we can define this function. We can define a function f of kn is equal to lambda on 2 pi cn. Okay, so we take all of this thing here and roll it up into a function. So lambda on 2 pi Cn is equal to f of Kn. And now we have a sum that looks like this. And if we take the limit as dkn goes towards 0, which is the equivalent of taking the limit as lambda goes towards infinity, then we get this integral here. And we're dropping the subscript n for convenience. And so the function f of x then can be written as an integral from negative infinity to plus infinity of f of k e to the ikx dk. And this is the integral that we anticipated previously. Okay, so that's great. Now we have f of x written as some integral over f of k. Can we write f of k in terms of f of x? In other words, can we find an inverse relation to this integral here? So here's our integral f of x equals some integral f of k. Now let's find f of k as an integral over x. So for the Fourier series, remember we had this integral here, each Cn is equal to k naught, and then this integral over the domain. And we also have this definition here for f of kn is equal to 2 pi lambda on 2 pi Cn. So this gives f of kn is equal to Cn on k naught. So in other words, we can write f of kn is equal to this integral here. And in the limit that k naught tends towards 0, that is the limit that lambda tends towards infinity, then we get this integral here, dropping the subscript n. So here we have an integral f of k is some integral f of x e to the negative kx. And up here we have an integral for f of x, 1 on 2 pi, integral f of k e to the plus kx dk. And these, in fact, are the forward and reverse Fourier transforms. So for some function of space x, the Fourier transform into spatial frequency is given by this equation here. So f of k is this integral. For a function of spatial frequency k, the inverse Fourier transform, so back into space, is given by this equation here. A word in the notation, this course will try and use capitals for functions in Fourier space. So capital F for a function of Fourier space, and lowercase letters for functions of real space. And the Fourier transform will represent with this curly f, and the inverse Fourier transform will represent with this curly f to the -1.